Hey guys, Mr. Gucci here to lead you through the first part of the 4.1 notes. All right, this is the first of our videos for chapter 4, and for section 4.1, we're talking about electromagnetic radiation. So, what is electromagnetic radiation? Electromagnetic radiation is energy that travels in the form of waves. Okay, this includes things like visible light, X rays, infrared, UV radiation, radio waves, all of these are forms of electromagnetic radiation. Important to know that electromagnetic waves have to be massless. They have to be capable of traveling through a vacuum. So things like vibrations of an earthquake are not electromagnetic waves. Things like sound and noise, those have to travel through air. All right, so that is not electromagnetic radiation. On the other hand, the sun gives off a lot of heat, a lot of light, and a lot of UV radiation, all of which can reach the Earth despite the fact that the sun is millions of miles away and there's nothing but vacuum in between us and the sun. So electromagnetic waves are capable of traveling even through vacuum. All right, they are essentially vibrations in the fabric of reality itself, like a pebble dropped into a pond, but that pond is the fabric of space and time. Okay, so gamma radiation is another type of radiation. Now, these electromagnetic waves are literally, they are waves, all right? They are waves in the same way that ocean waves are waves, or if you ever watched like an explosion and seen the blast radius just move outward, or if you ever like shaken a blanket and watched like a wave go through the blanket. Now, there are different parts to a wave. Okay, the top of the wave is called the crest, the bottom is called the trough, and the middle we call the origin. But the most important part of a wave is the wavelength, which is literally the distance, the length of a single wave from either the top to the top or the bottom to the bottom. Basically, how long it takes to go through one entire wave. That is the wavelength. The height of the wave from the center is called the amplitude. We'll talk more on that later. But the wavelength is the most important type of information about the wave because it's the wavelength that determines what type of electromagnetic radiation you have. For example, violet light and red light are essentially the same light. The only difference is that violet light, the waves are slightly shorter, and our eyes interpret that as being purple. And in red light, the waves are slightly longer, and we interpret that as red light. In fact, even beyond visible light, you can get shorter than violet light. Any wave that is shorter than violet light becomes ultraviolet light. And we are no longer able to see it. Our eyes can't process that information, but the energy is there. On the other hand, wavelengths that get longer than red, they still exist. We just, again, are no longer able to see them. That's called infrared. There are some animals that can see slightly more colors of electromagnetic radiation than we can. They can see beyond purple and beyond red. They can see ultraviolet and infrared. All right, but we cannot. The amount of electromagnetic radiation that we can actually see with our eyes is fairly narrow. Okay, and here's the full spectrum. Okay, again, it is the length of a wave that determines what kind of electromagnetic radiation you have. If the wavelength is super short, like the width of a nucleus, that's gamma radiation, the most harmful radiation in the universe, all right? If the waves are slightly longer, say the width of an atom, those are X-rays, also very harmful, but we can expose you to them in limited quantities, all right? If you get like the occasional X-ray every few years, then you're fine. But you might notice that when doctors or nurses take X-rays, they have to leave the room and go behind a special wall that blocks X-ray radiation. All right, and you're like, well, how come they have to get protection and I don't? Well, in the exact same way that if you're just going outside to get the mail, you don't need to put on sunscreen. But if you're going to go out in the sun for hours at a time, you need to protect yourself from all the radiation you'll be exposed to. Okay, that, by the way, that radiation from the sun is ultraviolet radiation, whose wavelengths are about the size of molecules. Okay, ultraviolet radiation. That is the radiation that comes right after X-ray. Okay, so up next, we have visible light. So as the wavelengths get longer from ultraviolet, they eventually become violet, and now we can see that light. All right, those wavelengths are about the length of single-celled organisms like bacteria and protozoa and so forth. All right, and then we have the visible light: purple, blue, green, yellow, orange, red. And then as the wavelengths get longer than red light, we can no longer see it. It's called infrared, okay? AKA heat energy. Those waves are about the width of pinpoints, okay? Next up, we have microwave radiation, about waves that are about a centimeter long. So like as long as a bee, okay? All right, microwave radiation. And lastly, the longest radiation, any radiation that's longer than a few centimeters in wavelength, that's all radio. And radio includes everything from cell phone signals, Bluetooth, Wi-Fi, all right, basically anything that sends wireless information, anything at all is almost certainly radio waves, okay? Like TV broadcasts, radio broadcasts, Bluetooth, so forth, etc., okay? The wavelengths of visible light that we can see occur with wavelengths between 400 billionths of a meter and 750 billionths of a meter. Again, 400 billionths of a meter wavelength, or 400 nanometers, that's purple light. All right, we can see anything up to 400 nanometers. If it gets smaller than 400 billionths of a meter, then we can no longer see it. That's like black lights. Like black lights are 380 nanometer wavelength. We just can't see it, which is why they don't light up a room. Okay? On the other hand, over here, infrared, that's about 750 nanometers. Any wavelength that's longer than 750, like 800 nanometers, our eyes cannot process that information. We cannot see it. Okay? Now, you will have to convert wavelengths from nanometers into meters. And if you go and watch the homework video, I do a sample problem of that, where I go out of nanometers into meters. I do another one where I go from meters into nanometers using dimensional analysis. Remember, a nanometer is a billionth of a meter. So 1 meter equals 1 billion nanometers, okay? And then we did this in class. Let me do one of these for you, all right? Can I convert 578 nanometers into meters? I can, all right? And I'm going to open up a little doc, and I'm going to do that here. So 578 nanometers into meters. Let me convert that. So 578 nanometers. And I want to convert that into meters. Okay? Well, remember dimensional analysis, I want to get out of nanometers, so it should go on the bottom. And I want to turn it into meters, which I can. And from the notes, all right, 1 meter equals 1 billion nanometers. All right, I'll just do it as scientific notation because that's easier. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 times 10 to the 9th nanometers. Okay, so basically I'm taking 578 and dividing by a billion. All right? Remember, you don't need dimensional analysis to tell you how to multiply or divide, just to let you know when you are multiplying and when you are dividing. So I'm going to go here. All right, I'm going to go here. I'm going to do 500 and, what the heck was that again? 578 divided by a billion. All right, so 5.78 times 10 to the negative 7th meters. All right, let me just double check that. A billion, 1 times 10 to the 9th. Yeah, 5.78 times 10 to the negative 7th. 5.78 times 10 to the negative 7th meters. All right, that's it. 5.78 times 10 to the negative 7th meters. Okay, that's the answer. So if you're going from nanometers into meters, you just divide by a billion. If you're going from meters into nanometers, you're going to want to probably multiply by a billion. Okay, so there you go. I just delete everything. Okay, bam, there we go. All right, back to the notes. So we talked about wavelength. Okay, another aspect of electromagnetic radiation is frequency. Okay, frequency is another aspect of electromagnetic radiation. The frequency is how many light waves or energy waves move by you every second. How many waves pass by every second? Now, all light travels at the same speed. So if waves are shorter, you're going to be hit by more waves every second, like an ocean with sharp, choppy waves, like a stormy sea. On the other hand, if the waves are longer, all right, then you are going to have fewer waves hit you every second. The unit for frequency is hertz, which just means every second. So if, for example, you might know that your computer monitor might be rated at 60 hertz. What that means is that your computer monitor can put up 60 pictures every second, and you register that in your mind as a smooth moving image. Okay, but it's actually 60, or in some new cases, 120 pictures every second. Now, frequency for perhaps one of these violet waves right here, it might be 700 trillion waves per second, because these are really tiny waves and they are moving very, very quickly. Okay, so we're going to figure out the relationship between wavelength and frequency, and it's going to involve the speed of light. All right, because all electromagnetic radiation travels the same speed. Okay, so the speed of light is 3 times 10 to the 8th meters per second, 300 million meters every second. Light moves really fast. All right, then there's the wavelength, which is the length of an electromagnetic wave in meters, and then the frequency, how many waves pass by each second. Now, all electromagnetic radiation travels at the same speed, okay? So if wavelength goes down, that means if you have shorter waves, you're going to see more waves every second. On the other hand, all right, if your waves are longer, you are going to have less waves per second. So as wavelength goes up, frequency goes down. As wavelength goes down, frequency goes up. I use the analogy to compare this to trains on a train track. Okay, now all trains have to travel the same speed, right? Because they can't pass other trains. If you go too slow on a train track, you're going to get hit by the train behind you. If you go too fast on a train track, you're going to get you're going to hit the train in front of you. So all trains have to essentially go around the same speed. Okay, now take a look here. Imagine you're stuck at a train crossing, like maybe the one in front of the Giant downtown. Okay, so this train's going to go by you. If you have trains with longer train cars, well, the length of the train car is longer, but you are going to see, as a result, fewer train cars pass by you every second. Okay? Fewer train cars pass by you every second. On the other hand, if a train comes by with shorter cars, well, each individual train car is shorter, but as a result, you're going to see more of them go by you every second. Now, the fascinating thing about this is if you take the length of the train, all right, and multiply it by the number of trains that you see go past you every second, you're going to get the speed of that train. And you know what? This train down here, if you take the length of this train, which is shorter, but multiply it by the number of train cars that come by every second, you will get the speed of that train, and those speeds are going to be identical. All right? And that's how this formula comes about. If you can take the wavelength, which is like the length of a train car, and multiply it by how many train cars you see pass by every second, you will always get the same value, which is the speed of light. So this is actually a pretty easy algebra equation, all right? So let me do this sample problem right here. If electromagnetic radiation has a wavelength of 3.45 times 10 to the negative 7th meters, then what is the frequency of that wave? All right? What is the frequency? How many waves are traveling by you every second? If they are that long, all right? If they are 3.45 times 10 to the negative 7th meters long, then how many waves are going to pass by you every second? Let's do that calculation now, okay? So what I do is I start out with this equation. Speed of light equals the wavelength, and that's the symbol we use for wavelength. That's Greek. This guy right here is called lambda, all right? It's also the half-life symbol, if you're familiar with the half-life game, right? You can also write it like this. Written like this. Oh, okay? Times the frequency, all right? Now, the speed of light, we know. It is a constant. It does not change. All right? The speed of light does not change. The speed of light is 3.00 times 10 to the 8th meters per second, okay? And according to this problem, we happen to know the wavelength of this light. The wavelength was 3.45 times 10 to the negative 7th meters. And so we have to find the frequency. We have to find the frequency. Now, this looks like a complicated problem, but it's not, guys. It's not, okay? It's not a complicated problem because this speed of light is just a single number. And this wavelength right here is just a single number. This is no more difficult than me asking you, hey guys, 6 equals 2 times what? All right. Oh, well, that's easy. I just divide by 2. All right. Yeah, this is 3, right? Well, guess what? This problem is just as easy as that, okay? It is just as easy. It's just that we're using scientific notation numbers. So I'm actually going to decide to use a slightly different format of scientific notation. I want to get frequency by itself. So I have to divide both sides by 3.45 times 10 to the negative 7th. And I'm going to use that E that we learned about before. Divide by 3.45 times 10 to the negative 7th. Okay, so I can do this. In fact, it's easier for me to do it in Google. So I'm just going to open up a new tab, and I'm going to say, all right, the speed of light, which is 3.00 times 10 raised to the 8th, divided by 3.45 times 10 to the negative 7th. What does that equal? It equals 8.70 times 10 to the 14th. All right? 8.70 times 10 to the 14th hertz. Okay, so that is the frequency. So what this is saying is that if you have light, oopsie, get this yellow. If you have light with a wavelength of 3.45 times 10 to the negative 7th meters, by the way, that's 345 nanometers, that's ultraviolet light, then you are going to be hit by 8.70 times 10 to the 14 waves per second. That's what hertz is. Hertz is the number of waves per second. Waves per second. Okay, that's 870 trillion waves every second because these waves are super small, but they're also moving super fast. Okay, guys, so we're going to call this part 1 of the video notes, and we're just going to be done with it, okay? Good. All right, expect part